Hello, so in this very final part of AS Pure, Year 12 Pure, this final part of this chapter, we're going to look at basically modelling with logarithms. In particular, we're going to look at something called linearisation, which basically means we can sort of convert a non-linear function into a linear one, i.e. a straight line, okay? So turn into a line, basically. So we can use logarithms to do that. So let me just go over what we mean by that then. So firstly, let's take an exponential. Y is ab to the x, right? X is my exponent, right? That we've seen that, right? We've seen exponentials. What we can do is we can take logs. Okay, I'll call that number one. So that's my first function. So I'm going to take logs. So if I take logs, log y is log ab to the x. Now again, as a reminder, a log with no base told is implicitly log 10. Okay, that's what we mean. So log just means log 10. Okay, we've seen that before, but yeah, another type of log of learn is log e. Okay, these are two particular types of logs you need to be familiar with. That's how we represent them. Anyway, we're going to be using log here. So we have this expression. Now we can actually simplify this bit here, log of ab to the x. I can use power laws. Firstly, notice I'm basically doing a times b to the x. I can remember I can split up a product in a log into two different logs by adding them. So log a, add log of b to the x. Now what can I do? I can then move the power x in front. So then if I do that, I get log y is log a, add x log b. Now let me rearrange this ever so slightly. So then log y is x log b, add log a. Okay. Right. So, what does this mean then? What does this mean? Okay, well, let me then say that big Y is equal to log little y. Let me say that big M is equal to log B, and then big C is equal to log A. If I use these substitutions into here, log Y is big Y, and then I get x log b. Well, log b is m, so that was mx, and then log a is big C. Well, what do you know? This is actually a straight line. This is actually this is now in straight line form. Y is mx plus c, right? With these variables here. So we can plot log y, which is sort of my dependent variable, right? That's basically y, but now log y. X is still x, that's okay. Log b is sort of the gradient, right? And log a is the number, it's the plus c at the end, right? You can spot that then. This is a straight line equation, okay? So what we've done here is we've converted this exponential equation into a, well, logarithmic one, but a straight line equation instead. What we can do here is basically we can convert between the two forms, and then we can convert from the exponential form to the straight line form here. Okay. Right. Another type of equation we can linearize is actually a polynomial. So y is ax to the power n. So now x is my base, right? It's a polynomial such as 2x squared or 5x to the 4, something like that, right? It's a polynomial expression. And we can do the same thing. So if I take logs, log y is going to be log a, x to the n. If I take logs on both sides, then I can split up this log by power laws, log laws. So log y is now log of a, add log x to the n, right? I'll split up the product into different logs. And then lastly, I can bring the power n to the front. So what do I have now is log y is now log a, add n log x. And then if I rearrange a little bit, log y is n log x, add log A. And again, if I then use a substitution, if I say big Y is log Y, big X is actually now log X, big M is N, and big C is log A, then again, if I use all these variables and I substitute it into this equation, okay, well log Y is big Y equals N, which is M here, at log X, which is big X, plus log A, which is C. Again, what do you know? I've converted it now into a straight line form, mx plus c form, right? So again, what I can do here is I can convert from a polynomial into another straight line equation, right, involving logs, right? You can see that with these sort of substitutions, right? So what I can do here is I can plot the straight line here. Now it looks really weird, obviously we've got all logs and different stuff, but hopefully the substitutions are making clear it is a straight line. In particular, we can plot log y against log x here, okay? Instead of y against x, it'd be log y against log x. Same way here, with the exponential log y, we can plot against just x, okay? And yeah, and so basically this is linearisation. We can take logs to get an exponential or polynomial into straight line form here, and then plot the line and then do some stuff with the line, right? But yeah, so that's what we'll be essentially doing in this section. Okay, so here in this example, I'm given a table which gives the rank by size of the population, the rank by size and the population of the UK's largest cities. London is ranked number 1, but it's an outlier. Okay, so we're just given some data, right, in this table, and we're told that the so-called relationship between R and P, the rank and the population, is given by R is A P to the N. Okay, A and N are just constants, right? They're just unknown numbers. Then it says for part A to draw a table given the values of log R and log P. Now we're given the values of P and of R and P. So if I just do a rough, if I just roughly copy the values, R is 2, 3, 4, 5, 6, and then P is a million. Then 730,000, and then 620,000, and then 530,000, and then 480,000, right? Right, so that's the values of R and P given in my table. Then it wants me to draw a table with the values of log R and log P. So what I essentially need to do is log all the values here. So firstly, log R, I'm going to do log 2, right? Now remember, again, that's log base 10, technically, right? Log base 10 of the values. So if I do firstly log 10 of 2, I get 0.30 to 2 decimal places, okay? So that's 0.3. Then log 3 would be 0.48. Then log 4 would be 0.60. Log 5 would be 0.6. That round up to 0.70. Okay, and then log 6 is 0.78. Okay. Okay, rough little table there. That's the values of log R if I literally log all the values. Now log P, again I'm gonna do the same, but for these values here. So firstly log of 1,000,000. That's going to just be 6, okay. Then log of 730,000. That's 5.86 to 2 decimal places. Then if I do 620,000, I get 5.79. And then if I do 530,000, I get 5.72. And then if I do log of 480,000, I get 5.68. Okay, so that's my table of values, right? And actually you can kind of see sort of the convenience now for taking logs, because logs basically makes things more sort of standardized, more closer and compact together. Because here we've got large values, right? We've got 1,000,000 to like 480,000. But here we're only between 6 and 5.68. That makes it a lot easier to plot the graph of log versus the normal values, which can be quite big and variable. Okay, so that's the table values. Then part B is indeed then to sketch the graph of log R against log P. Right, so firstly we've got our table values. So log R is going to be on the top here. So log R, it starts on 0.3 to 0.78. So 0.3 to 0.8, right? It may be best to, if we start at 0 then, let's go up in 0.05. So that would be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9 on 1. Okay, so 1 there, then 0.9, then 0.8, then 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, and then 0.1. Okay, so I've gone up in 0.05s, or every 2 boxes 0.1. Okay, that's a scale I've chosen. So yes. Okay, so then log P, as you can see here, quite interesting. The values are between 6 and 5.68, right? At the top end it's 6, at the lower end it's 5.68. So what I can actually do here is, because the values are kind of just fixated around 5.6 and 6, it doesn't really make sense to start from 0. What I can kind of do is I can do a little squiggly line like that, right? And then what that means is there's like a break. There's a break in the axis between 0 and then I'm going to start at 5.6. Okay, that'll be my starting point. Okay, that's what this zigzag means. I'm kind of interrupting my axis because I want to start. I don't want to start at 0. I want to start at like 5.6 and then start my scale from there. Okay, and then I'm going to end up at 6. So I can do that if it makes sense here, because there's only a certain interval of values. It's not starting from 0 really. It's starting from like 5.5 to 6. Anyway, and then I'm probably going to go up in 0.02. So this will then be 5.62, 64, 68, 7. I'll mark that. Then 7.2, 7.4, 7.6, 7.8, 5.8. And then 5.82, 8.4, 8.6, 8.8 at 5.9. And then 5.92, 9.4, 9.6, 9.8, 6. There we are. Okay, so that's my scale of choice, and then that would be log P. Okay, that's on the sort of x-axis, right? It's log R against log P. Okay, and so yeah, so simply then, if we're going to plot log R against log P, so we're going to take our table values right here. So firstly, again, log R 0.3, so that's going to be along here, right? That'll be when log P 6. So 6 is at the very end. So it would be there. That's my first coordinate. Then 0.48, that's going to well, 0.48 against 5.86. So 5.86 is here against what was it, 0.48. So it'd be somewhere there, right? So again, that's 5.86 if I squeeze it there, and that's 0.48 along log r. Okay, then if I then plot 0.6 for log r, 0.6 is obviously here, against 5.79, that would be roughly there, right? Just there we are. And then 0.7, so again it's going to be here now, 0.7 if we go along to 5.72, it's going to be here, right? Then lastly 0.78, that's going to be roughly there, just under 0.8, against 5.68. So that would be here. Okay, so I've plotted my points then, log r against log p. So drew sort of the coordinates, right? Then I'm going to draw and then draw a line of best fit. Okay, so a line of best fit will roughly go through the points, and you'll notice it'll be a straight line, right? Roughly. So if I sort of marry up my points against this ruler here, again, a line of best fit will roughly be in the middle of all the points, so it looks something like this. Here, right? Roughly line of best fit there. Okay, cool. Then for part C, use your graph to estimate the values of A and P, A and N. So remember, this is my equation for R and P. So if I restate that down here, part C, R is equal to AP to the N. Okay, that's R and P, but here in this graph I got log R and log P. So I'm going to take logs. You'll notice a very common strategy to just take logs for these questions. So log R is going to be log AP to the N, and then it's going to be very, very similar, pretty identical to sort of what we did at the start. So then log R is going to be log A add log Pn. Well, of course, the N can come to the front, so it'd be add N log P. And so log R is simply N log P add log A. And then notice this is in straight line form, right? Log R, N is my gradient, so I'll call that M, if you will, log P. And then this plus C at the end, this is sort of my y-intercept there. Right, so log R is sort of my y, right? Log P is sort of my x. And you can see that here, right? I've plotted log R against log P, which gets me a straight line. Well, this is in straight line form. So I can sort of compare then. I can read off this equation here, right? This log R, N log P add log A. I can compare the ideas with the straight line. So this is the equation here, log R against log P. I've drawn the graph. Well, it's a straight line, roughly, the best fit, right? So firstly, I can calculate the gradient, right? And actually, the gradient, we don't really need to estimate the gradient, right? Because obviously it's a line. Obviously, it's a rough line of best fit, but we don't need to estimate the gradient because we know precise points already. We know all these points, right, on this sort of line here. So the gradient, we can just use the table, right? If we just pick two points, two table values. So let's take log P is 6, so the coordinate 6 for log P and log R is 0.3. I can take that point, right? And I can take, let's say this point here, right? And then 5.72 for log P and 0.7 for log R. So if I literally then compute the exact gradient between the 0.6 and 0.3 and 5.72, 0.7, so no estimating required, right? To guess what the points are on the graph, I can use the values given. If I calculate the gradient, again, that's then going to be changing y. So, well, obviously not y here, but log r. So 0.7 take away 0.3. Then the change in sort of the x, if you will. So that'd be 5.72. Take away 6. If I work that out, that would get me a gradient of negative 10 over 7. Right? Okay, and also then the sort of the intercept then. So where it crosses, well, not the y-axis, but sort of the log r axis, right? We can kind of see it's 0.9, right? That's going to be 0.9, right? And so then I've got my values then. So again, if I compare with my equation here, then actually n is the gradient. Well, we just saw that the gradient is negative 10 over 7. So I can say that this is equal to that log r is equal to negative 10 over 7 log p, and my sort of my intercept of 0.9. So add 0.9. Right, and so then if I literally compare these two equations, then substitute in my gradient and the intercept of the line, right? If I compare these two equations, I can compare that n has to therefore be minus 10 over 7, and log a has to be 0.9. Right? Hopefully you're with me there. And so therefore, well, n is just n, right? But I need a, but I've got log a. So then what I can do to find a, I can take base 10, I can take powers of 10, so I can raise everything by 10, so 10 to the power of log a is 10 to the 0.9. Well, again, log is just log 10, right? So sort of the 10, the exponent 10 and the power and the log 10 cancel out, they're inverses, so simply a is 10 to the 0.9, and that's it. And then to two significant figures, then if I were to give that to two significant figures, this n here, minus 10 over 7 to two significant figures is minus 1.4, and a, well, is 10 to the 0.9, which is 7.9. Okay, and actually that means that now we can actually work out the exponential model fully, because we know what n and a are. That means r is now a of 7.9, p to the minus 1.4. And so that's kind of where the beauty of this sort of linearization approach, taking logs approach, where we have an exponential model, we can work out that model by taking logs, and then we can work out any missing values in this way. So now we've got the exponential equation, right, that we started off with. Okay, I should say as well, this was from the textbook, the example they go over. The textbook's wrong here. Well, I believe so, because they did the opposite. They sketched log p against log r, so they got a different graph, and the gradient and the intercept was wrong. It should be log r against log p. Okay, because the question says plot log r against log p. That basically means y against x. So the y-axis should be log r and x on log p. And also because r, with the original equation, r is sort of the y, and then p is the x. So it makes sense for r to be y and p to be x. So if you're a bit confused, I'm pretty sure the textbook's wrong with when they how they went over this example, but here we are. Okay, so we've got this question now. So here I am now given the graph of log p against t, okay, and the graph represents the population of bacteria, p over t hours. The graph has a gradient of 0.6 and meets the vertical axis at 2 here, right? A scientist suggests that this growth can be modelled by p is ab to the t, okay? A and b are constants. First of all, it says write down the equation for the line, okay? This line here, so this is literally just y is mx plus c. But here we don't have y, we have log p. So log p is going to be the gradient, so it's going to be mx plus c, but m, the gradient firstly, is 0.6, so it's going to be 0.6, well not x, but t, okay? T is on the x-axis, t, and then add the y-intercept, well, the log p-intercept of 2. So that is simply my equation, okay? No need to overcomplicate it, that's it, okay? Now, it says, using my answer, part A, find the values of A and B here in my exponential model. So, to go from this linear line equation to the exponential equation, I can do it 2 ways. I can either literally take logs of p of this equation and end up with this log equation here, but actually I can go the other way as well by taking exponentials. So here I have log p again is 0.6t add 2, and so again the log is a base 10, so I'm going to actually raise both sides by 10. So 10 to the log p is 10 to the power of 0.6 add 2, it's t add 2. And so again the base 10 cancels with the log 10, and so we simply get p is equal to 10 to the 0.6 t add 2. And that's it. So it is in this equation here, but actually what I can then do to get it exactly in that form, I can use power laws to split this split the 10 up here. So p is 10 to the 0.6 times 10 to the 2, right? Hopefully with me there. This is just simply the power law. A to the power m times a to the n, we add the powers, right? So here we're adding 0.6t and 2, so I can split up in this way to get 0.6 times 10 to the 2. And actually 10 to the 2 is just 100, right? 10 squared is 100. So I can say p is 100 times 10 to the 0.6t. 0.6t there. And now hopefully spot this is exactly in this form here. So if I were to compare it with p is ab to the t, well, or otherwise, or alternatively a times b to the t, right? Then hopefully you can spot that very simply, that therefore A has to be 100 and B is 10 to the 0.6. Okay? And that is the value of A and B. And then the three significant figures, well, A is 100, that's fine. Then B, 10 to the 0.6. If we were to put that in the calculator, we get 3.98 to 3 significant figures, and there we are. Cool. Okay. Then it says part C, interpret the meaning of the constant A. Okay, so I'm gonna sub these values of A and B into the model. So P is AB to the T. Well, we know what A and B are now. P is 100 lots of 3.98 to the t, and it wants me to interpret A. What does A mean? So again, interpret means relate your answer to the real life problem. So in here, this question is talking about a population of bacteria. Okay, what does that mean in relation to the population of bacteria? This value of 100 here, right? So A is 100, and so what that means is, again, we looked at this before, but if we then just consider t is equal to 0, then p would be 100 lots of 3.98 to the 0 Of course, anything to the 0 is 1, so I'm simply left with p is 100, and so the number 100 is the initial population of bacteria, the initial value of p, which is the initial population of bacteria, and that is it. Okay, cool. Yeah, I think that's everything. Okay, there we are. Okay, so we're going to look at some exercises, but really I'm just going to look at exam questions, because I think with these modelling questions, exam questions are the best practice. What we're given here is the time, t seconds, of a pendulum that takes to complete one swing. The time it takes for a pendulum to complete one swing is modelled by the formula T is AL to the B. So a pendulum is kind of like a wrecking ball, right? It's like a bulldozer. It swings up then down, and it just kind of repeats that sort of motion of going up and down. Something like that. You don't need to know what it means here particularly, but that's what a pendulum is. It's given by this formula, right? T is AL to the B. Okay. I'm gonna do capital L because it's just gonna look like 1 otherwise. AL to the B, and L is the meters in the length. So there we are. So I always underline the units. Okay, underline the units for t seconds and L for meters. They might catch you off guard. Okay, so it says part A. Show that this relationship, in other words the formula, show that the formula can be written in this form here in terms of logs, right? So what I notice is, well, I'm just going to take logs of both sides, right? So then if t's AL to the B, then log t is going to be log AL to the B, and then I can split up this again, so this product in the log here, so it's going to be log A add log L to the B, and then again this power B can come to the front of the log, so log T is log A add B log L, and actually if we just rearrange it ever so slightly, then log T is B log L add log A, and that is the equation they want. There we are. Cool. So that's part A. Part B. Now we're told a bunch of information, right? And actually, just blah blah blah. They basically recorded the values of log T and log L, and they've got this straight line graph. Okay, this is the graph of log T, right? Log T against log L, right? And we've also given these 2 points here, right? So with that in mind, it wants me to find a complete equation to t is AL to the B. In other words, it wants me to find what the missing values A and B are, right, in this equation here. Right, so if we, right, so if again we compare, if we sort of look at this equation we got here from part A, we can see that log T is essentially Y, B is, log L, right, is my X, right, log L, B is going to be my gradient M, and log A is going to be my C, so my gradient is equal to B, and my intercept is log A, right? Okay, so firstly my gradient, right? I can calculate the gradient, so that's going to be changing Y, changing X. So if I remind you, the 2 points I'm given on this graph, 0.21, 0.45, and then minus 0.7 and 0, then the gradient between these 2 points, okay, well, you can think of it as changing Y, so 0 take away 0.45. Of course, it's not Y, it's log T, but if it helps, it's kind of what we're doing. So 0, take away 0.45, then change in the x, so minus 0.7, take away 0.21, if I just put that in the calculator. I get 45 over 91. Okay. And so that's b, right? Therefore b is equal to the gradient, which is equal to 45 over 91. Okay, so what I can do here is I can substitute b into here. So then log t now is b, which is 45 over 91, log L, add log A. Right, there, okay. Now, then log A, as we discussed, is then the intercept of this line here, the line of the graph here. Well, I'm not given the y-intercept, unfortunately. Obviously, we can see it here, but it crosses this axis, right? But we're not given the point. So what we need to do then is kind of just substitute another point in to find a log A. So let's substitute, probably best to substitute this point in, right? It's more simpler, right? So if I sub in the point minus 0.7 and 0 into this log equation here, then what I get is my log t, which is my log t is sort of the y coordinate, right? So 0 is going to equal 45 over 91 log L, which is sort of the x value of minus 0.7, add log A. Then simply I can solve for log A. So 0 is going to be, well, 45 over 91 times minus 0.7 is minus 9 over 26. Add log A. And so then log A is 9 over 26. And then to find A, I can, obviously it's log 10, right? So I can raise everything to the power 10. So 10 to the log A is 10 to the 9 over 26. And then the 10 and the log cancel, so A is 10 to the 9 over 26. And then as a decimal to 3 significant figures, that would be 2.22 to 3 SF. And then if we then also convert B here into 3 significant figures, well, 45 over 91 is 0.495 to 3 SF. And so that is the value of A and B. Okay, that is B. And A is here. Cool. So there we are. Then it says, with reference to the model, interpret, again, that key word, the value of A. So what does the value of A mean in reference to what's going on? So the pendulum swinging, right? So actually, if I then restate this model, so T is AL to the B, well, we know what A and B are. T is A, which was 2.22 of L, L to the B, which is 0.495. Okay, so we've got the equation here. Now, what A doesn't mean in this case, it's not the initial value. It's not when, say, L equals 0, right? It's not when L equals 0. If you set L to 0, then T would be 2.22, lots of 0 to the 0.495. Well, we're multiplying by 0, so T goes to 0. That tells me nothing, right? So what A does not mean here, 2.22, that's not the initial time, right? That's not the initial value. So it's quite a trip up, this question. Actually, what we need to consider is actually that if L equals 1, not 0, if L equals 1, then T is going to be 2.22 to the 1 to the 0.495. Well, 1 to the anything is 1. So this is simply now 2.22. Okay, so it's all about kind of figuring out how did we just get 2.22 from the equation, right? So now, that's what that means, right? 2.22 is when L is 1. But what's significant about L equal to 1? If we look at our model, L is the length of the pendulum, right? And then T is the time it takes for a pendulum to complete one swing. And so basically that's saying that essentially when the length of the pendulum is 1, so when the length of pendulum is 1 meter, right? The time it takes for one swing is indeed 2.22 seconds. And that is what 2.22 means, that number in this model here, okay? Quite confused. I think quite confusing that is, I think. It's quite a bit different to normal, but hopefully they made some sort of sense. How we worked out what A meant here by considering L equals 1, and so that gets me 2.22 for T, which is the time. Okay, so when the length is 1, the time is 2.22 essentially. Right. Okay. Okay, so we've got another question here. So again, we're given a graph. So the value of a rare painting in V pounds. The value is given by V is PQ to the T. P and Q are constants, and T is the number of years since January 1980. Okay. Right. And we're given the line L, and we're also told quite nicely the equation of the line is log 10V is 0.05T add 4.8. Right? So we're given quite generously the equation of the line as well. Then it says find to 4 significant figures the value of P and Q. Right? So what we're told essentially is we're told the exponential equation, and we're told the logarithm, this straight line here. Well, what we know is we can take logs of the exponential equation and we can kind of get it into this form here. We've seen that, right? We can linearize, turn the exponential into this log form here, right? Which gets me the straight line. So I'm going to take logs. So V is PQ to the T. If I take logs of that, then log V, which again is log 10, right? Log V is log of PQ to the T. Take logs of both sides. Then I can split up the log here to say that, well, log V is log P and log Q to the T. And again, then I could bring the T as a power to the front of the log. So log V is log P add T log Q. And if I rearrange slightly, log V is T log Q add log P. Now, let's compare that with this straight line we're given. Let's compare this straight line we're given, the equation, with this equation here. Okay, well, firstly, log V matches with log V. That's great. Then T matches with T. Cool. So then that means that firstly 0.05, the coefficient of T, has to correspond to log Q. Right? So then I can say 0.05 is equal to log Q. Then I'm also, if I go up, then this number 4.8 has to correspond to the number at the end, log P. So also 4.8 is equal to log P. So at that point, then we're just solving these two log equations, right? So again, these are log base 10. So that means then if I raise it by 10 each side, take exponentials, 10 to the 0.05 is 10 to the log 10Q. And then the exponential 10, the log 10 cancel. So Q is 10 to the 0.05. And similarly, 10 to the 4.8 here is 10 to the log 10p. Again, the log cancelled with the 10. So p is 10 to the 4.8. And so we've got our values of Q and P here. And so the four significant figures, if we put that in a calculator, 10 to the 0.05 is 1.122 to four significant figures. And here 10 to the 4.8. And so this is 63095.73, but obviously then to four significant figures, that would be 6309, but then the 9 rounds up to 1, so effectively that would be 63,100 to four significant figures. And there we are. And so that is my value of P and Q. Cool. Okay, then it says, with reference to the model, interpret. So again, that key command word, exam word, interpret, meaning explain what the number means in relation to the real life scenario. So in relation to the value of the painting, right? What does the constant P mean? Okay, well, P is this. If I restate the model then, so part C, is it? If I restate the model, so V was PQ to the T. Oh, so it's part B. PQ to the T, but P is 63,100. Q, which is 1.122 to the T. Right, so again, then the value of P, which is the 63,000 here in front, that's the sort of the initial value, right? That's going to be when, if I set T to 0, then V is going to be 63,100 or 1.122 to the 0. Of course, anything to the 0 effectively goes to 1, so that would just be 63,100. Okay. And so yeah, so this is the initial value of V, right? Or the initial value, more specifically, of the value of the painting. Okay, you'd be fine with that, but actually, more specifically, T0 is actually T0 in the year 1980. So actually, more specifically, the value of the painting at January 1980, or 63,100 is the value of the painting at 1st of January 1980. Okay, and there we are. Okay, then second part, obviously now we need to interpret what Q means, so this 1.122 in here. So what does that mean in relation to the model? This is harder to see, but again, we went over this. Once you practice this sort of thing, it's the same sort of idea. But the idea is this. We saw that when T0, then V is just 63,100. What if we then increase by 1 year? What if then we say T is 1? Then V is 63,100 times 1.122 to the 1, right? That's when T is 1. Then it can go to the next year when T is 2. Then V is 63,100 times 1.122 squared. Then if we do the next year after, hopefully you spot the idea, V is now 63,100 times 1.122 cubed. So what do you see noticing? Each year, we're multiplying the value by 1.122. And then obviously the next year after, from year 1 to year 2, is another 1.122. Then from year 2 to year 3, we multiply again by another 1.122. And so this 1.122 is a multiplier, right? So 1.122 is the multiplier for which the value, the V, which is the value of the painting, is multiplied by every year. Okay, every year, obviously when t increases, right? Because t is years, right? T is years. So when t increases by 1, so every year, that is what we're multiplying the value by this 1.122 here. Okay, hopefully it made sense. Also, you could also visualize this multiplier in terms of percentage increase, right? Think back to G to C. Actually, 1.122 as a percentage, if we times by 100, right? Move it 2 points forward, that'd be 12.2%. So actually, alternatively, you could say, or the value is increasing by 12.2% each year, every year. Okay, and they're the same thing. Okay, so as you can see here, hopefully you just see it's a multiplier, right? We've seen this before, that the value here, right, the value being multiplied by rate, being raised by t, right, is a multiplier. So we multiply each year by the same amount, 1.122. That's how exponentials work. Be timed by the same amount every year. That's the whole lot of exponentials. And so that's the multiplier. Okay. And so yeah, it's quite standard, this sort of explanation, once you get used to it. But we've seen a few questions now, but that's what that means realistically. Okay, so that's what the values of P and Q mean. Then it says for part C, from the value of the painting predicted by the model on the 1st of January 2010. So it's given me a specific time, a specific year. Now, again, the first year is 1980, right? So how many years have we gone from 1980 to 2010? 30, right? So this is when t is set to 30. That's what I'm going to substitute into to get that value at that year. So I'm going to sub t's 30 into my model, my equation v. Here, v is 63,100 of 1.122 to the t. So then when t is 30, that will be 63,100 of 1.122 to the 30. And if we just put that in the calculator, we get 1,994,278.043. Okay, that's the exact number. So 1,994,278. So that's my exact number, but it says to round it to the nearest 100,000. 100,000. That is this number here, 900. That digit here, that's 900,000. So if I was to round that, then that would go up. Right, that would increase. That would round up because obviously the 9 next to it would shift it up by 1. So 1.9 million will go to 2 million, right? So which equals 2 million to nearest 100,000. And so therefore the value, so then the value in 2010 then, right, in 2010 when t is 30, is indeed £2 million. Okay, and there we are. The human population, p billions, is modelled by p is ab to the t, where a and b are constants and t is the number of years after 2004. Right? And using the estimated population from 2004 to 2007, a graph is plotted of log p against t. Now they've not given us that graph, but they've just told us they sketched it. And the information they told us is the gradient is 0.0054 and the intercept is 0.81 on the p-axis, log p-axis. So anyway, so part A, they told us to estimate the value of A and B. Right, so again, A and B in this exponential model here. Again, it's talking about a graph of log p. So we're going to need to take, well, log p, right? So we can take logs of both sides. So log p is going to be log of ab to the t. Again, then we can split up the log. So log p is log a add log b to the t. So then log p, if I move the power t in front, so log a add t log b, and then I can rearrange a little bit to log p is t log b add log a, and then recognize it's another straight line. And so this is log p, that's cool, that's sort of your y, right? T is, well, just t, that's sort of your x. Then log b is going to be the gradient, right? Mx, and then this will be the intercept c. So we can read off from here that the gradient again is going to be log b, and the intercept is log a. Okay, but we're given the information about the gradient and the intercept, right? We know that the gradient is indeed 0.0054. So 0.0054 is equal to log b, the gradient. And also the intercept is 0.81. So 0.81 equals log a. And so we can solve these two equations to find b and a. So we can take powers of 10. So again, 10 to the 0.0054 is equal to 10 to the log b. Again, log is base 10 by default here. So the log and the 10 are cancelled. So b is 10 to the 0.0054. And then if we solve for a here, take powers of 10 again. So 10 to the 0.81 is 10 to the log a. Again, the log cancels, so a is simply 10 to the 0.81. There's my values. And then to 3 decimal places, right? 3 decimal places. If you just put that in the calculator, well, 10 to the 0.0054 is 1.013 to 3 decimal places. And then if we put 10 to the 0.81, we get 6.457. And those are my values. Cool. Then it says, in the context of the model, interpret the values of A and B. Okay, very sort of standard question again. So P, so if I restate my model now, P is AB to the T, but we know what B and A are. So then P is 6.457 times 1.013 to the T. And so again, firstly, the value, what the A, interpret what A means. So again, what is going on? It's talking about population in billions since 2004, right? So the world population. So what does A mean? Again, if we were to then set T to 0, you'll spot it's the initial value of P. So P is going to be 6.457 times 1.013 to the 0, but anything to the 0 effectively is 1. So P is just 6.457, the initial value. So this 6.457, which is A, is the initial population. So 6.457. Now, remember, it's in billions, right? The population in billions. So 6.47 billion is the, well, not the initial population necessarily, it's initial value, but it's when T 0, which is year 2004. 2004. So it's the world population, which is P, in 2004. And there we are. And actually, if you think about it, it kind of makes sense because I think we're at 7 to 8 billion now. I'm not too sure, I think, but it's kind of in the rough ballpark. So that figure does sort of make sense. Then that's what A means. That's what 6.457 means. And then what we need to interpret is now B. What does B mean in relation to the real life situation of the population here? So again, B, likewise with the last question, it's to do with multipliers, right? So again, to illustrate, we know that when T0, P P was 6.457. Then after 1 year, T is 1, P is 6.457 times 1.013 to the 1. And then when T is 2, again another year after, it's 6.457 times 1.013 squared. So you can see again, we're effectively multiplying each year by another 1.013. And so it's again a multiplier. So 1.013 is the multiplier for which the world population is increasing by or multiplied by every year. And that every year is essential to add on at the end, because obviously that's what's happening. Every year we increase by one value of T 1 year. That's what it's multiplied by, this 1.013. And again, alternatively, you could be more specific and say, well, this multiplier as a percentage, 1.013 is 1.3%, right? If we times by 100, and that's by a decimal point. So alternatively, or you could say 1.3%, or the population increases by 1.3% every year. By 1.3% every year. Okay, there we are. Cool. Then it says for part C, use the model to estimate the world population in 2030. Okay. So again, now a sort of substitution exercise. But 2030, again, the initial value of T is 2004, right? So how many years have we gone from 2004 to 2030? 26 years, right? So if we sub in 26 into my model, where are we? So I'm going to sub T is 26 into the model P, which was what? Here. P is 6.457 to the 1.013 to the T, was it? Yes, okay. And then when T is 26, that would be 6.457 to the 1.013 to the 26. If we put that in the calculator, we get we get 9.034 to, let's say, 3 decimal places. So what does that mean then? So that's the value of P, but obviously it wants the world population. So remember, population, I underlined it here. The population is P billions. So it's the value of P times a billion, right? So world population is simply 9.034 billion. Okay. Okay, so then part D, we're asked to comment on the reliability of the answer to part C. Right, so part C was the world population in 2030, right? Now, the model is actually between 2004 to 2007, right? That's kind of where the model is reliable at, between these years, right? That means if we use the model to predict the population at years after 2007 or before 2004 or after 2007, it's no longer reliable. It's what we call extrapolation, right? If you would have seen this in statistics, extrapolation is where it's sort of outside the range, right? Which means 2030 is outside the range. It's after 2007. It's extrapolation. Now, that means it isn't reliable, but If it was, say, like a few months, right, after 2007, there'd still be a bit of like a grace period where it'd still be a bit reliable if it's just after 2007. But actually 2030 is it really is outside the range. It's a good few years after, 26 years after, right? So the model is only between these 3 years, but we've gone 26 years after that. So it's quite a big time gap, so it's heavily extrapolated, so not reliable at all, really. So for that reason, we'll say so model isn't reliable as it is only between the years 2004 to 2007, and actually 2030 is a lot of time after 2007. So it is it's sort of it's just not reliable, essentially. So it's unreliable it basically is far away from the range, from the time interval, right? And so yeah, and you could say it's heavily extrapolated, which isn't reliable. Okay, so there we are. So that is it. So that is this video. That's the end of the chapter, and indeed the end of AS Pure that I've covered. So yeah, so that's it for now. I'll see you next time.